Welcome to this explainer, where we're going to embark on a seriously mind-bending cosmic journey. We're going to zoom out as far as physically possible to figure out exactly how vast our reality really is. So buckle up, because the scales we're about to talk about are going to completely change how you view our place in the universe.
So, where does the universe actually end, and what happens if you somehow hit the edge? To tackle this massive existential question, we need to start small and literally scale our way up, step by step, right to the absolute limits of known physics. Okay, to set our baseline for the sheer scale of space, let's look at this number: 4 years. It takes an entire 4 Earth years for just a single photon of light traveling at the absolute maximum speed the universe allows to get from our sun to our very closest neighboring star. And honestly, that is just a microscopic baby step in the grand scheme of things.
Zooming out just a little bit within our own solar system, we hit the furthest known object. It's aptly named Far Out, and it sits 132 astronomical units away from the sun. Just to put that into perspective, it takes light a whopping 18 hours just to graze its icy surface.
But our system's true gravitational boundary? That stretches out so much further, to an incredible 60,000 astronomical units, forming the hypothetical Oort cloud. Effectively, you'd have to travel a full light year through space before truly breaking free from the sun's grip and hitting actual freezing interstellar emptiness.
Now, what's really wild here is the sheer difference in density. Out in our local neighborhood, things are pretty empty. We've got about 1 star per 10 cubic light years. But at the center of the Milky Way, you've got 1,000,000 stars packed into that exact same amount of space. If we lived there, the night sky would look like a constant blinding fireworks display. Though with all those supernovas going off, it would be insanely dangerous. We're talking needing thick concrete shields just to survive the radiation.
Let's keep zooming out. As we do, this incredible structure starts to build. Our Milky Way, which spans 100,000 light years, is just one small part of the local group. That merges into the massive Virgo supercluster, which itself rests inside the colossal Laniakea supercluster, stretching an unfathomable 520 million light years across. We are literally just specks of dust inside a cosmic Russian nesting doll. And deep inside that nesting doll hides the Great Attractor. Sitting 250 million light years away, this mysterious focal point is entirely hidden behind the thick dust of our own Milky Way's plane. It acts like a giant cosmic magnet, dragging countless surrounding galaxy clusters toward it. And the craziest part is, we still don't fully understand what it is, simply because we can't get a clear look at it. As we push even further out, we start finding structures that literally break our understanding of physics. Check out this number. Discovered in 2013, the Hercules Corona Borealis Great Wall is a superstructure 10 billion light-years across. It is so impossibly huge that its mere existence shatters our current theories about how the universe evolved after the Big Bang. There just shouldn't have been enough time for something this massive to form.
Zooming out again, we finally hit our visual edge: the metagalaxy, or the observable universe. See, because the universe is about 13.8 billion years old, the light from anything beyond this boundary simply hasn't had the time to travel through space and hit our telescope lenses. So it's not a physical wall, it's just the absolute limit of our cosmic vision.
But wait, if the universe is 13.8 billion years old, how can the observable part be bigger than that? Well, while all those photons were traveling toward us, the very fabric of space itself was constantly expanding and doing it faster than the speed of light. Because of that continuous stretching, our observable universe is actually a staggering, giant sphere about 93 billion light-years across.
And this brings us to a brilliantly shocking twist that scientists confirmed back in 1998. The universe isn't just expanding. For the first 8 billion years, gravity was actually winning the tug-of-war, and that expansion was slowing down. But then, something bizarre happened. It stopped slowing down and started pushing apart faster and faster, actively accelerating.
It turns out, the culprit behind this acceleration is what we call dark energy. It's a massive mystery that physicists are still desperately trying to figure out. Basically, this dark energy acts like a giant cosmic anti-gravity engine, forcefully repelling galaxies away from each other and overpowering their natural gravitational pull.
And it behaves in such a paradoxical way. We're used to normal gravity, right? Where the closer objects are to each other, the stronger the pull. But dark energy is the exact opposite. It acts like this bizarre, invisible spring. The further apart galaxies get, the more forcefully this anti-gravity pushes them away, generating more and more empty space.
Okay, so as we finally cross the boundary of the observable universe and step into pure theoretical physics, let's talk about the actual shape of it all. Imagine a bug crawling on a globe. For that bug, the space is finite. There's a set amount of surface area, but it's never going to crash into a wall or fall off an edge. Our cosmos might be set up exactly like that. Except instead of a 2D surface, we're living in a boundless 3-dimensional version of that globe. Theoretically, if you shined a super powerful flashlight into a boundless closed universe, the light could eventually wrap all the way around the cosmos and hit you right in the back of the head. Scientists have actually looked for this, but we haven't observed it yet, probably because our globe is just too incredibly huge for light to have made the full trip.
When we try to understand these boundaries, we inevitably run into the weirdness of dimensions. We experience 3 normal dimensions, stuff you can measure with a ruler. But the quirks of gravity hint at extra compactified dimensions. Think of it like a fishing line. From far away, it looks like a simple 1D line. But look through a magnifying glass and you see it's a 3D cylinder with a surface. Extra dimensions in our universe might be rolled up into tiny microscopic loops just like that.
This whole concept was born from the struggle to unify the gravity of massive objects with the quantum mechanics of tiny particles. The result? The fiercely complex 11-dimensional string theory. It pictures a universe with our 3 normal dimensions and 8 compactified ones. The only catch is, right now, it's basically pure math. We simply don't have laboratory instruments capable of physically testing it.
So what actually lies beyond the metagalaxy? Completely unbound by the need for observable proof, theorists go wild here. Some propose a metaphysical, timeless void. Others suggest we're just one bubble in a boiling, infinite multiverse, where every neighboring bubble has completely different laws of physics. And the most radical thinkers? They argue our entire reality might just be a highly advanced computer simulation run by a super-civilization. Mind-blowing, right?
As we wrap up, I want to leave you with a thought that is both terrifying and incredibly majestic. If dark energy keeps accelerating, eventually the space between objects will expand faster than the speed of light. All our neighboring galaxies and eventually stars will vanish beyond the cosmic event horizon. Future observers would look up into total endless darkness, thinking they are completely alone in an empty void. Really makes you realize how incredibly lucky we are to live in an era where we can still witness the majesty of the cosmos, doesn't it? Thanks for joining me on this explainer, and stay curious.